Okay, for people who are joining our live stream, this is a design meeting about some features for machine learning in Wolfram Language. Basically, we're talking about anomaly detection and missing imputation. So let's start off. What is this p-value thing? I mean, do we not have an analog of p-value already in our statistics system?
Probably.
What isn't it a CDF? Isn't it related to the CDF?
Yes, it is related.
Yeah.
How is it related? What would this return? P-value of normal distribution, 0.6. What should that return?
So that would return the probability to have an event that is rarer than whatever 0.6 is.
And that
so it would integrate the right tail, but also the left tail. So sometimes I call it double tail p-value. I realize that, yeah. Okay.
Yeah. What's the relationship between that and the CDF?
So
or do we need our statistics folk here?
Actually, I was thinking we could invite someone in statistics because I think it's Sasha that have been very interested in land distribution when he just learned about it a few days ago.
Okay, fine. Well, let's get them here, please. You do that?
Gosha is on her way, but Andrea couldn't get hold of Roger yet.
Okay, what about which Sasha?
Alexander Pavlik.
I don't think he is available at this time.
Yeah, I don't think so either.
Okay.
But Gosha is here.
Okay.
Hello.
Okay, so first question for you, Gosha. P-value of a distribution. How do you compute that from the functions that we have? Hello, are you there?
Well, the p-value, we don't have it defined on the distribution, but you have the CDF, so the cumulative.
Yeah, I understand. So look at the screen and tell me whether this is what does this mean? P-value of normal distribution, 0.6. That would return what? It would return the probability that the actual value would exceed 0.6. Is that correct?
There's two of them. There's one-sided and double-sided, I would say. For my purpose, I only consider the as many-sided as possible value. So the total probability of
but you're outside of that region.
Exactly, and the region defined by the PDF of 0.6.
Yeah, okay.
It's kind of a stretch. I don't know if it's just us that called it p-value because it seems like an extension of the p-value with unidimensional distribution.
P-value, it's used in the hypothesis testing, so that gives you the probability is that your values are outside of.
Yeah, I know what the definition is. I'm trying to find out how we compute.
There is a function in the hypothesis testing.
Yeah,
it's right here. Hypothesis test data.
Oh, sorry.
Right. So it can also be the value of the survival function. Depends which tail we're looking at and whether the hypothesis is one-sided or two-sided.
Okay. All right. Well, okay. Let's understand. By the way, we got a bunch of background noise here. Sounds like a seashore. And I'm kind of thinking that's Gosha.
There is a construction going downstairs.
No, that's not what it sounds like. It sounds like some misconnected, wrong amplification. Anyway, no matter. Okay, so maybe you can put yourself on mute when you're not
I'll try.
Involved. Okay. All right. But so okay, let's go back then to this anomaly detector function. Okay. So I don't understand why this is not called anomaly detect. What is that?
No, this is something that is already trained. You have detector function, an example, and rather than having a true false, we want to know, oh, actually, what was the p-value? Because the way it works is that you compute a p-value from an example, and then it's compared to the acceptance threshold.
Right. Okay. So the question that you're asking here is, if the distribution was a normal distribution, what is the p-value associated with an observation of 0.6? Is that correct?
That's what I want the string property p-value to return, yes.
No, I understand, but this is the minimal case of that, right? This is the case with with a fancy, I mean, alternatively, I could say p-value of learn distribution of blah, blah, blah.
Yes.
Comma.
Yes, and an example. Yes. So this was a side thing. So first I want to know how we call it in the context of an detector function. And then I thought, oh, maybe we should do something like PDF.
Yes. Well, I think that makes sense.
But I don't want to overuse a term.
No, we should not use it incorrectly. So we need to figure that out from the statistics side of what the right way to do this is.
I never found, I mean, I looked a bit.
Okay, let's not address, we've got...
Just so Claudia knows, I never found something for multivariate. Everything I find for p-value is like unidimensional distribution and, you know, one-tailed or one-side tail, double-side tailed p-value.
What we have is for any type of distributions that we learn.
So maybe there's another term in statistics for that. I didn't find it.
Kosher, any ideas?
I mean, so the question of the multivariate distributions is that, what's your value? In a way, like how you're moving along the axis, right? Because in the case of the univariate,
I understand. It's clear that there's an obvious notion of being greater than that value.
Right.
Yeah.
So that's the issue, and also that goes together with the fact of how quantiles are defined, and the issue of how to think about this region, for the quantiles. So that's
how is CDF defined for multivariate distribution?
Excuse me?
How does CDF define for multivariate distribution?
It's it's a multivariate function. So you have the probability that your x and so your x is less and your y is less than some.
So it's on the coordinate axis.
Yes.
So to speak.
Yes.
So I mean, one could imagine some weird polar CDF or something, right? Because what you're saying is what's the integral of that distribution within some region, right?
Mm-hmm.
Yeah, so I guess you can imagine many of them. Yeah. Gaussian spoke about quantile. It's very related to quantile, this p-value stuff.
Well, so it's CDF, obviously. Yeah, right.
Inverse kind of, yeah. Mm-hmm.
But in the sense that quantile do not have... Wait, I'm losing...
What is the quantile? What's the multivariate generalization?
Oh, sorry. No, I was confused. No, it's the same. Yeah, okay.
Okay, so look, one thing that's coming out of this is the potential utility, just because p-value is such a famous thing to compute, of supporting that for univariate distributions just in a form like this. Gosha, can you comment on that?
I was on mute. I think that's confusing. I mean, we have all the necessary functions defined for univariate distributions. And
okay.
The p-value, it's I really don't understand what you would like with the p-value on that, to understand what it is, because it's connected to the hypothesis testing. So there is some hypothesis. So in here, that what are you asking for, really?
Yeah, fair enough. Okay, so then,
are you asking that your normally distributed variable it's greater than 0.6, smaller than 0.6? I mean, I just equal 0.6. I just don't know.
It's rarer. So the question that we have for anomaly detection is not the probability that is bigger or smaller or anything of the sort. It's a probability that is rarer.
So that's going to be the survival function at this point, because survival function gives you the probability that your value is greater than 0.6.
How do we encode?
No, not x below 0.6. It's an expectation of PDF of x below the PDF of 0.6.
That's the same thing, isn't it?
No. Here you just integrate from 0.6 to minus infinity. Ours, you integrate over the parts
this is
that
probability.
are the PDF.
Okay. I mean, so there's a function one could imagine having, which is something like this, where the second argument is a function that says, so for example, it could be greater than 0.6. Right? We could imagine, I don't think it's correctly called p-value, but it's I'm not sure if this is the right thing either, but something like function expectation. Right? It's just a shorthand way of asking for something like this, but it dovetails with, I think, a little bit more closely with what the machine learning case wants to be.
But that's exactly the CDF. I mean, when you look, it's
not exactly the CDF, because this could be any function I want, right? That's the whole point. The greater than is just one example. You could put any function you want there. And so this is the same as saying, what's the expectation of that function applied to x, with x being normal, x being distributed according to that.
That's not what we need for p-value. Again, okay, p-value is an integration of the origin that have a PDF lower than the PDF of 0.6.
Right, but that's what you do. If you do compute expectation, you integrate with respect to the PDF.
Okay, let's zoom out for a second before we get too deeply into this. Maybe you could show, okay, so let's review what these are doing. So we've got an anomaly detector function.
Yeah.
And
basically a learned distribution inside.
Right, and then we're going to, and the question is, what is it returning in this case? It's returning the probability that this example or worse, if I'm not mistaken,
yes,
could occur.
Yes.
Okay, so I think the name p-value is wrong here. I mean, what you're saying is probability of a rarer example. That's the full name of this.
I mean, in my case, that's what I meant by p-value in this case. Yeah, probability of a rare example.
Yes, that is correct.
Simple as that.
Okay, who knows what that, I mean, is there a name, rarer probability? I don't know. I mean, what it is it's a more extreme example. That's what you want to know.
In a way, yeah.
Is it more extreme or is it rarer? Those are two different things.
It is rarer because we don't speak about metrics here. We don't speak about an example that is bigger or smaller. We only think in terms of probability of
okay.
appearance.
So it's the integrated probability of all rarer events.
Yes.
Okay. So anybody, we've got multiple other people on the phone. Somebody must have a good idea here. Integrated probability for rarer events. What should that be called?
Do we have example?
Yeah, why don't you guys show an example?
Do you want me to show the anomaly detection?
Yeah, go ahead.
I mean,
or you want to show it, Etienne?
I have something just to explain. Okay, maybe I can just share quickly.
Yep.
I'll just show quickly exactly here. I'm going to get just a 2D data set so we can visualize what's happening from the iris data set. So I'm going to take the sepal length versus the petal length, and here is the scatter plot.
Okay.
And length distribution. Fine. Going to plot distribution for the contour plot. Okay, so that's a learned distribution, and in red, that was the data. So basically, if we take this data point, and let's imagine the data point is actually on this contour.
So explain to me for a second, sorry, how does this relate to estimated distribution, what you get here?
So
could I have used estimated distribution for this as well?
Yes, with a proper model, I guess.
No, because this is non-parametric, right? What you do, it's non-parametric estimation, so it kind of looks like one of the data distributions.
Yeah,
so smooth kernel distribution or kernel mixture distribution, probably.
Actually, I think it used the kernel. Yeah,
it used the kernel distribution, right? Yeah, kernel. Yeah, so you have here the kernel density estimations, which are probably using the standard Gaussian kernels for that. Yes.
Yeah.
Okay. All right. Fine.
Information.
Magnificent.
These are the. Oh, actually, it doesn't show.
Okay. All right. Okay. So anyway, so now we have that distribution. Okay.
Yeah.
So now what you want to do is you want to state a sepal and petal length. And you want to say, what's the integrated probability that you have something for that sepal and petal length? You know, it sits in somewhere in the ocean there. Let's say 7.3 or something, right? I put a point at 7.3, right? What your question is, that will have some probability density value at 7.3. And you're saying integrate all of the places in this universe that have less than or equal to that probability density value.
Exactly. So a bit like if you were doing the contour plot that passed by this point, and you were integrating, so integrating the PDF, of course, of everything that is outside this.
Okay, so who knows what that should be called? Is there anything in the literature for what that should be called? Is James here? Does James know?
Sorry, no.
I'm not sure there's a name, but it is one extension possible of p-value.
It's a pretty, yes, but I think it's a, okay, so let's try to capture what it is that we're talking about here. So what we're talking about is integrated rarer probability. Is that a correct statement? Or
so that's
rarer CDF.
So that's survival function, right?
Is it? I don't know. I mean, isn't survival function, I mean, I've heard that used for very different kinds of things.
But it gives you the other end.
I know, but that's like for univariate distributions, isn't it?
It's defined for multivariate as well. But that's integrated.
What about the name
PDF on the other side?
Right. What about the name rarer CDF? And the description would be, or is that crazy?
I mean, CDF means you're, I don't know, integrating from, you know, that you have a metric where you're integrating.
It's survival function. It's an integration of the PDF. It's just a different side. Right, you see this in the notes.
Right.
So that's exactly your thinner tail of the PDF. You know, like above certain. So the question is, if you know, if this is what you're looking at, because CDF is a cumulative on the PDF, right? So you have the values, but the thing that I'm trying to connect, because we're talking about events. That's one space, probability space, and then we're talking about the values in PDF. That's a different space. That's where we are in the reals, or you know, whatever the space is with numbers, right? So I'm trying to connect, and so the thing is that rare events in the probability space they correspond to the events to the low PDF value, right?
Yep.
So this is, you are in a tail, what we call the tail of a distribution, right? And then the question whether your events, the rare events, are, you know, probable, or not, then we have these distributions with what they're called fat tails and such.
Yeah.
Right. And so I'm trying to kind of connect what you need, because if you just need to integrate, PDF on the other side, then CDF, then we have survival function that's already exists.
I understand, but the point about, look, the term survival function suggests a time axis of some kind, because that's where that name came from. We simply don't have that here, because we might have, these might be pictures of cats and dogs, and this space might be, 300 dimensional.
It might be text. It might be
right. So I'm going to push again. Integrated rarer probability.
Okay, let's write it down for now. Integrated rarer probability.
Rarer.
Yep.
And quotes.
I found integrated a bit too mathematical for somebody that just use anomaly detection.
Okay, all right. So let's think about that. But so what this is, well, we could just say total rarer probability.
Yeah, total.
Yeah, I like total rarer probability. I think it sums up quite nicely and simply what you're trying to say.
Actually, yeah, it's explicit at least.
Okay.
Or just rarer probability.
Well, then you lose the idea that you're doing an integral.
Yeah, I think you will need the total, because I think the rarer probability, the whole point
it's actually the probability of having a rarer event. So coming from distribution.
Okay, but so what about rarer event probability?
I like it a lot. And rarer or better example.
Rarer data.
Machine learning will speak often about example. Rarer data probability.
What about just rarer probability, which is, I think, what was suggested before?
Yeah. Rarer. I think that I like rarer probability. I mean, in the context, let's see.
Yeah. So we're asking the question, what is
example rarer probability? It will be used in that. Oh, we have to see how it's be used as well, right? It's going to be used like this. Anomaly detector function, an example.
Okay, so it is the probability for something rarer to occur.
Yeah.
I think total would be helpful. Total rarer probability. The total probability for something rarer than this to occur. You just write that down. Total probability for something rarer than this to occur. For something rarer than example.
Yeah.
You might also consider the word cumulative if you want to avoid total. And then cumulative goes together with the other side.
Yeah, the problem with cumulative is again, it suggests a very one-dimensional notion. I mean, cumulative, maybe. I don't know. I think total rarer probability is decent.
Yeah. Why not? I would still skip the total, because when you speak on every day, when you would be like, oh, what are the chances that I don't know, that I will live older than 90 years old?
Yeah.
You don't say what are the total chances, or what are the total probabilities that I live.
I know, but that's again a one-dimensional case. What you're saying is, look, I think you need total. Here's why. Okay? You've got a distribution of cat pictures, right? You showed a picture of an elephant, right? It's not the case that there's a one-dimensional thing that goes from cats to elephants. Instead, it's there could be an elephant, there could be a potato, there could be a tree. Each one of those has a rarer probability than that elephant. And so this is the integrated probability of all of those rarer pictures, which I think is in the case where you're in one dimension, I agree with you, but we're not. We're dealing with it's a slightly bizarre thing. I mean, it's saying in this whole space, that's a complicated multidimensional space, I prefer this. I think, okay. I think we've got
I think also with wording like what is the probability that we live to an age above 90, the above 90 implies a sum, whereas in the case of an image, or the difference between two images, there's no nice wording that implies a sum like that, and that's
yep. That's right. Okay.
Right. Give you back the screen.
No, wait. Why are you giving back the screen? I want to see miscommunication next. So well, what was the
Amir had some examples. Me, I just add
Okay, let's take a look at that, because what we are talking about here is the way to handle missing data.
Yeah.
What is that?
PDF. No, it's just a PDF. This will be the sampling. This will be the sampling. So here so basically this line distribution, they know how to do PDF query, sample, and imputing missing values.
Well, and you can also do the mean of that distribution, can't you?
No. In that case, you could, because it's numeric, but because it's intended to be arbitrary spaces, we didn't implement mean or things like
just so I understand, other statistical things that are it requires some kind of super robust statistics to be able to work in these weird spaces, I would think. Is there a notion of a median?
No, because there's no...
If you define PDF, then you kind of can derive the properties for the PDF, right? So you have the corresponding variables. So in that sense, you can compute mean for this distribution. It doesn't mean that you're going to have the mean of the pictures. That's on a different space. So when we talk about here, showing the PDF, you see it's in terms of X, Y being numbers. Right, so for that you can compute.
No, but this is a particular case where it's numerical data. If it's a cats and dogs pictures thing, the mean of the cats and dogs pictures.
But that's what's your distribution on the cats pictures? Is it not numeric?
No.
Yeah, I mean the cat could be, because we for example conform the images before, so then it's kind of a defined numeric space. If we didn't conform the images, then it would be a bit weird, because all images are different sizes. So there'd be a weirder space. But in the case of text or things like that, then the space is not numeric at all. And so we don't have mean, we don't have median, we can just sample, compute, expectations maybe.
Could you just pull up the page of statistical computations?
Can I also just quickly point out that while mean might not necessarily make sense in a lot of cases, for example, if you have categorical data, mode is often a useful
mode.
Works
mode exists.
So that's commonest. That's what we call commonest.
Yeah.
Right.
What do you want? Probability and statistics? Which guide?
Yeah, just probability and statistics. Let's look at that. And let's look at, scroll down. Where is it? Scroll up. I guess random variables. Go to the random variables section there.
Mm-hmm.
Distribution-related functions.
Yep. So this we have.
Well, just click on that. Click to that
this
page.
We don't. So we have PDF. We don't have CDF. We don't have this.
And why don't we have... on this page, why don't we have commonest? Do we have commonest as a Gosha? That will be a question for you.
That's going to be the descriptive measure, so descriptive statistics. Probably if you go back to the.
It doesn't work.
It doesn't exist for distributions.
Mm-hmm.
Commonest has two items.
Yeah, and it doesn't exist for distributions.
Yeah.
Why not?
Because
for the data.
I mean, first of all, it's not super well defined. It requires a unimodal distribution. Second, there is a choice of what we support for these functions, and it's very expensive to support additional ones. Now you talk to Etienne, he only supports one, which is PDF.
Okay,
out of 35, there's 35 of these, okay?
35 watts?
Of these properties that you have for distributions.
Yeah, where are those properties?
If you go back, there moment, there's another sub guide page for moment-related things and so on.
I'm having a hard time finding stuff here. Special moments is not where I would look to find the variance of a distribution. Can we go back to that first guide page for a second? This is about probability and statistics. I'm surprised that things like mean aren't here.
This is for random variables, not probability and statistics.
Scroll up to
This is descriptive statistics.
Can you go one back? Then you're gonna.
Oh, that's random variables. Okay, that's wrong. Yeah, okay. So there you've got. So there we've got mean and variance. But where is the stuff about descriptive statistics?
It's its own guide page down there. Related guides.
Okay. All right. Go to related guides. But it seems like probability is the top first of the related guides.
Oh, yeah.
Descriptive.
But it seems like I'm just pointing out that from a page that says probability and statistics, one would think one could get to that more easily. It's a minor point.
That's a long debate, and we can have that debate.
Okay, all right, okay. But let's not deal with that right now. Okay, so could we go back? I'm sorry, go back to that page again, please. Okay. So my question is, which of these are plausibly supportable for these wild learned distributions?
I think commonest. And okay, for this one, I think only commonest. Now, anything that use metric is bye-bye. Entropy. Yep. So, oops. It's
so these are very data oriented as opposed to sort of, distribution oriented.
Well, yes, commonest. What would commonest mean? Commonest means if you've got the cat picture distribution, what does commonest mean? It means
I think commonest for a distribution would mean if it's a unimodal distribution, it's the peak of it.
Well, I understand that, but I'm saying for cat pictures, we've got a distribution of cat pictures. What is
a cat that is most likely?
The most likely cat.
Yeah.
Which is the same thing as the whatever we're calling it, data synthesis, or what are we calling that now?
Yes, the design was data synthesis. Yes, we didn't implement it yet, but it was design choice.
Random data synthesis.
Oh yes, right.
Random data. Okay.
And what is the difference between random data?
Random synthesis. Random synthesis.
What is that? Is that some random variate, sort of another name for that, or?
Yes, it's a random variate of a learned distribution.
Okay.
It's a child of learned distribution. Just learn to reproduce data.
Actually, I don't understand why that isn't simply random variate of a learned distribution. So, for example, for cat pictures, what's the difference between random synthesize of cat pictures?
So, we could have just not have this function. It would just be random variate. I guess if we have this, it would let the user give his intent to only use the distribution for generating.
Yes, all right, fair enough. So that's random synthesis. You give it a big loss of data, which could be weighted data of pictures of cats, including how favorite the cats are, and it will then generate a pseudo cat, so to speak.
Yeah.
Okay.
So
So then commonest means what? In the space of cats, it's the winning.
Well, if it's a mode, I would interpret commonest as being querying the mode. So the value that at the highest PDF.
Well, it'd be interesting to see what that actually is for cat pictures. Is it something sensible or not? Or, for example, for the MNIST thing, Amir, can you say for the MNIST data set, can you say immediately what the mode of that is?
Well, we don't have something to compute the mode, but let's say I train a distribution. I can look on a test set, the one that has the highest value. But we don't have a way to... It's also not easy because it's an optimization process.
I understand. It's an optimization process with respect to the parameters. What this would presumably do, people have done this with neural nets, right? Is like, what is the best elephant picture or the most elephanty elephant picture, if I'm not mistaken? Is this useful? Is my question, to find the mode of the cat distribution, so to speak.
I don't think it's really useful for this case.
Okay.
In general, I'm a believer that samples are as good or even better for most application than mode. People like to maximize though and get the map, for example, for missing imputation. Okay, typical case. Okay, that's where we'll need the mode actually. You have some missing data, you want to impute them.
Yes.
So we can condition distribution and then a choose choice. Either you get a random sample from this condition distribution, or you get the mode. It's typically people like to have the mode in this case, which I'm sure in many applications it makes sense. I think in others you're fine by having a sample.
So there's one really big use case for having samples, which is multiple imputation, where you impute multiple versions of the data set and run your analysis multiple times, and then aggregate the results of those analyses to get a better idea of sort of variance in your imputation results.
Yeah.
Okay, we have a number of interesting comments on our live stream here, which let's just address for a minute, and then we're going to talk about missing imputation and representation of missing data. So somebody's asking about causal inference, and I don't know what DO calculus is. They're asking about our plans for causal inference. Etienne, can you say something about that?
There's no plan at the moment. I guess it will come quite later. I think it's not a short-term thing. Probably we'll work on probabilistic programming before, graphical model before, and then...
Fair enough. Okay.
And there's some simplest thing that I don't know about, but it was quite low on my list. It's quite low on my list.
Roger, do you have comments on that?
No, not really. I do think both graphical programming and probabilistic programming are really quite important.
Right. Okay, another comment. Probability density PR of x has dimensions of 1 over x. If you transform x to f of x, where f of x is a nonlinear function, contours do not correspond to the contours of p of x. Okay. The comment being made here is the definition of rare probability density is coordinate dependent. Yes. I mean, in other words, if you make a coordinate transformation on your,
Yes.
But I don't. But is there any useful meaning to that? I mean, in the space of cat pictures, what on earth is the coordinate system? I mean, what is the metric in the space of cat pictures? Do we have to define that, or we must have to define that?
We define it by conforming the images, and then we just take this numeric space. So they all have the same dimension, the images.
Yes.
And they have, for example, in that case...
So you're basically, you're saying that they are a bag of pixels, basically,
yes,
of this conformed space, and then what? And then it's basically a...
That's the space where we... So yeah, it's...
so what's the distance between
dimensional? The distance, it will be I mean, depending which distance, but the Euclidean, it would be
I see. It's the Euclidean distance between those high dimensional points, which means that the probability, it's coordinate dependent. What the...
Yes. That's why it's not super well defined. Nevertheless, in practice, so if I look at the PDF of this stuff, by the way, this is most likely out of the 100 example that I put. This is the PDF of this stuff. Now, if I take a random image, I think I fixed the underflow problem. So, this is enough to say that 10 to the 600 is bigger than 10 to the minus 300,000.
And you can do log PDF on that. It would be a small number.
That is an anomaly. So we do the hypothesis for anomaly detection that what's relevant is a PDF in the space that the data are given. But you could trick it by changing the coordinates and suddenly make some things more anomalous and some things make less anomalous.
Yeah, well, that's obvious. I mean, it's obvious that if you transform even if you do image transformations, you can clearly change something, yeah, you can change it around. So fine. So it's coordinate dependent. We should probably make sure that that's a note in the documentation.
Mm-hmm.
Someone is complaining that there's a root mean square, but there isn't a mean squared. Do we want to comment on that, Roger? Do we want to comment on that?
Say that again.
We have a function root mean square, but we don't have a mean squared function. Is that simply because, do we have mean squared operating on distributions?
No. What is mean square?
The square of root mean square, I think.
Yeah, well, arguably you could just square the root mean square.
Right. Okay. So, the caller is right. You often want that because, in optimization, you don't really want to use that square root on top there. You just remove it. I don't know. It's a suggestion for having another descriptive statistics, sounds to me.
Right. So can we, I think, Sushma, you're PMing here. Can you make a note of that?
Mm-hmm. Yes.
Separate discussion.
Okay.
Someone else is pointing out, more sophisticated users will prefer to train a GAN themselves directly to generate samples. Comments on that?
To train directly to generate samples?
To train a GAN, generative adversarial network. I don't know. I mean, we're providing something which is an easier packaging of this stuff. That's a fairly complicated thing to do. Okay, let's go back to the missing imputation stuff. Am I going to go back to my screen, or you can use your screen here?
I can. Yeah. Okay.
So what's the question here?
How do we represent missing data? So far we just use missing. For example,
didn't this relate to our whole annotation discussion?
Yes.
Well, we didn't finish that discussion, but so.
I mean, I said yes, I guess. So far, that's the type of thing we would feed to represent. Here is 2 numerical vector and missing at position 3, missing at position 1. Okay.
Do we have anybody from image processing on this meeting?
Carlo.
No, we have image processing. I think Piotr is also here, by the way. Yes.
Is Piotr here?
That's good.
He is here.
Okay, great. Piotr, can we hear you?
Do you hear me now?
Yes, we hear you fine. Okay, all right. Okay, so, all right, let's go back to my screen because I've also got the stuff from the previous annotation discussion. Okay, so the issue is we are trying to impute. So, for example, what is the name of the thing that fills in scratches? It's inpainting, right?
Yes.
How do you specify where you want to inpaint? I see. You just give a region to inpaint. Is that right? So
image graphics, yes.
I'm sorry?
Another image or graphics is basically a mask that is completely separate from.
Right, I understand. So that's one example. And in inpainting, that's one example of a place where you are effectively saying this is missing data that I want to impute. Am I right?
Yes.
And this has to be special. I mean, it has to be only black and white, I guess, the mask?
Yes, for in-paint binary mask, yes.
And are you saying in the case of missing imputation that you can have a non-binary mask?
It
no.
has to be binary mask. Yes.
Yeah. I was just wondering what you could give. I'm just trying to think in terms of general expressions because these 2 images are not like you could say. I mean, I don't think we want that, but to say only the first channel of the pixel 5 is missing.
I see.
And I'm trying to think in arbitrary expression. Could we express, that at a given location you have some missing?
That's a mess. Right. So, okay, but as you've said, one approach, and this relates to the general annotation thing, one approach is a mask. This I think, let's pull up again. Hey, Sushma, do you remember where I have the information on the annotation stuff?
No, I was not in that meeting, but let me...
Is that like the third time I've made that suggestion that you were there? Okay, so here, I've got my notes.
Okay.
Okay. So, right. So these are cases where we have markups of various kinds, including, for example, let's see. So here are some of the things we've talked about. The annotation rules possibility, where, and value. So that's saying in an image, I want to annotate that this is a picture of an elephant or something, right? That these pixels are, I want to carry around with the image the annotation that this bag of pixels represents an elephant. Am I making sense? Or in audio, that this, part of the time series represents the speaker, right? And so that would be an obvious way to carry around things like missing. I mean, that's a masking approach to missing. Okay, so you're saying, so let's enumerate the cases that we need to let's enumerate the cases that we need here, right? What types of data are we going to deal with here? We're dealing with image data. We are dealing with audio data
in general, for now.
Which includes image and audio, right? Yes?
For 12, we won't have audio for the distribution.
Okay.
We basically have everything that has a fixed dimension at the moment, yeah.
Okay, all right, okay.
And so no series.
What's that?
No series for now. No time series.
Okay, all right, fine, but that's not relevant to this design discussion. Okay. Yeah, I see, because you can't, I don't even know how you do that. Well, how do you deal with the distribution for an unbounded thing like that?
You can do that, so it will mostly, recurrent neural network type thing that will, so basically we'll decompose the distribution as being, the probability of the first element times the probability of the second given the first, times the probability of the third given the history, and so on.
That's like a chain of events.
That's how you model the distribution, and yeah, and that's kind of what we do for, for language models.
Yeah, I understand. Okay, so I see. Okay, so let's come back to, all right. So there are these cases where it is data dependent, where you're saying this thing in the data will be taken to be what? So, I mean, in general, this will be some kind of pattern thing, right? Here. You say if the data matches this pattern, you want to impute it.
Okay, that's one possibility, yeah.
I mean, here's a question.
Seems a bit hacky, but yeah.
Well, here's a question. Why is this called missing imputation? Why does it have to be missing? Why isn't it data imputation?
Okay.
I don't think that has to be missing.
Mm-hmm.
So if we said data imputation of the existing data, comma, and now we've got to say, okay, so we're either saying, where is the data missing? Is the data to be imputed? I mean, this is like, it's almost like an interpolation function where you're given some data and then you're told, you know, go figure out, well, what you're going to return from this is new data that's had those pieces added in, right? Or replaced, basically.
For this one, it will return a missing imputer. Now, if you do data impute, it will return the new data.
What's that?
If you do data impute, if you do the verb, it will.
I guess the difference between data imputation and missing data imputation is that in the case where there is missing data, you don't want to use that data to learn the distribution. Whereas in general data imputation, if you want to replace things, you might still want to use the values in the data set which aren't missing. I don't know if that makes sense.
I see what you're saying. So in other words, during the learning process, okay, so that's an important point. So do we parameterize that right now, Amir? Did you understand?
Actually, yes. Actually, we can have the option that we train, like we impute while training or not impute.
No, what James is saying is if there was data there, but we just...
Oh, I see. Yeah, it's like a double intent. Like, is this data relevant or not?
Should we include it in training or not?
Yeah, that's right.
Yeah, that's exactly what I was saying.
Yeah,
we don't have it right now, but...
Okay, fine. But then, so what we're saying is this data, we're trying to divide the data into two bins. Data that we're leaving, data that we're just copying from the original, and data that is to be replaced somehow, to be imputed. Is that correct?
Mm-hmm. I mean, yeah.
Yes, and the idea of having the name missing imputation was that by default, if you don't give it anything, and if it would be missing in the any missing pattern, so it would by default consider those as missing. This is
I understand. I think that's not actually. Sandra on our live stream is asking, why aren't we just calling this imputation rather than data imputation? And I agree that the word imputation, I don't know, impute, I'm not sure. Okay, but let's go back to this question about, we're dividing it into two bins. The bin of things that we're just copying over and the bin of things that want to be replaced.
Okay, when you mean things, you mean like there's some example that are in one bin and some example that are in two bin, in other bin? Because that's not what's happening.
No. Okay. I'm saying that in the space, these examples are living in some space. They're cat pictures with some, position for the nose of the cat or something.
And each of them have some missing values, yeah.
Okay. And then what comes back from impute? I don't understand what comes back. If you have got a collection of examples and you say data impute, do all the examples come back with the cracks filled in?
Yeah.
Okay. So, but what about if you want to give an existing distribution, like an existing image distribution, and then you just want to impute from the existing image distribution, like old.
I think what we agreed on the design was that the first argument would be a distribution. Data imputes the distribution, and then I think that's what we agreed in the design. But actually,
okay, and then what? Then what's the second argument?
That's then there will be the examples that are missing. So it will be a two-argument version of the data impute.
Wait. So you're saying that what we've got here is data impute of distribution, comma, and then the data, a single piece of data or multiple pieces of data.
Yeah.
And that should return new data that has.
So. That's what we had.
Okay,
makes sense.
It's very similar to except now the third question. So the question is, how do we represent what data, what pieces of data are to be imputed. So what we could do is the third argument here could be very much like it is in Paint, essentially a region of data for which to do imputation.
I think we should go beyond an extra argument, because in classify, let's say, I might also want to give images that have missing data. I don't know if it, of course, it's less common than in missing imputation.
Okay.
But why not?
Well, but so which aspect of classify? You're saying classify, you're saying that the thing that is coming in as the thing to test, the picture of the potential rhinoceros has part of the thing torn off. You say, is this a rhinoceros even though we tore off?
I mean, this for sure. For sure, we have missing data. I mean, data sets in general have a lot of missing values. So you keep on learning from data that have missing values and evaluating your model on data that have missing values. That's for sure. But it's true that most of the time the missing value happened when you have numerical and nominal data sets. So we didn't have a strong need to give an image with missing value. It's rare that you have data sets and you naturally have missing values in your image. But I was just saying for sake of generality, way to represent missing data, you know.
Right, but so what we've got for images in our proposal over here is some kind of...
what is that for sound, though?
I'm sorry?
Yes.
No, I mean...
I was thinking, I was thinking, actually, what happened to have images that are missing values or sound that are missing values?
It's also really common to have like tabular data, like say hospital records or survey results, which have tons of missing data.
Oh, this say all that.
Right, but we've got a mechanism for that. We've got the missing symbolic wrapper.
Exactly.
The problem is that it is inefficient and crazy to have the, every pixel in the crack be a pixel that's encoded with missing. Now, I think for images, we have talked about having some kind of NaN representation internally for the images. Is that not correct? Piotr, can you comment on that?
Well, definitely not in 12. We're using numeric array to represent image data, and we do not allow NaNs in numeric arrays.
No, I understand, but we're talking about going forward into the future. Are we going to do that and use that as a lookup table, the presence of a NaN as something which forces a lookup of something more complicated in the image, or are we going to do it differently?
Well, we haven't got to that point. We haven't had that detailed discussion. What are we going to do with images? There was only discussion with Mark Sopronio and compiler people that at some point we want to have not a numbers stored in numeric arrays. That's all it was so far.
Okay.
Can I just make 2 points? One is that using NaN as a missing value indicator can be a bit dangerous, because often you might do some sort of, the users might do some sort of pre-processing or something.
Yeah, which is arithmetic which generates a NaN. Good point.
Yeah, and then
the point of that, what I was saying is the NaN is not representing the data. The NaN is basically a way to not tangle up the innards of the system while saying there's something wrong with this pixel. And then you have to go look up in an external table what's wrong with that pixel. Did that make sense?
Yeah, I think I see what you're saying.
Okay, anyway, your second point.
The second point was that if you are worried about how to efficiently store information about where there are missing values, rather than using a full-fledged matrix, you could use some sort of sparse matrix representation, because I think in most cases, the amount of missing data will be much less than the amount of non-missing data.
I was thinking about that as well. It could be a list of position. And this would work for arbitrary expression. So maybe it's a bit cumbersome, but it could be like missing data. Then we put whatever expression, and then second argument, we put like a list of position where it's missing.
Well, that's the where, arrow, what annotation mechanism here. I mean, clearly.
Yeah, it is.
The position is very clean way of implementing this.
I mean, that might not be the best to.
Well, but it's okay. We could support both things. I mean, if you give it an image, it could figure out that what you mean is the positions of those pieces.
Should we have a wrapper? Like missing data, comma, and then we support various way to declare what's missing and where it's missing.
I think that makes sense.
Sorry, say that again.
Like, should we have a wrapper?
Where do we think we get images with missing data? Where does it happen in real life?
Good question.
Like the image that has a scratch.
No, that's a very obscure case, because I mean, where does it happen? It probably doesn't happen very often. I mean, things like dead pixels in a CCD array.
That's pretty rare.
I think it's more for removing something in a picture or like by hand. I don't think people.
Okay, I understand. So this is like, in Photoshop or something, you can go and you can just say, I want to remove that, random pimple on a nose or something, and it will just go and fill it in with stuff from around it.
Yeah, or the person behind me, and
yes,
just fill it up.
You can also imagine applications such as repairing photos that were semi-damaged in a fire or things like that.
Yeah, well, right. That's the case we're seeing with the scratch. But so the case of relevance, the case
that doesn't sound like a mainline case to me. It sounds like
that case is not a mainline case. The case of getting rid of photoshopping people out of images, that's pretty mainline. That's a routine thing done all the time with things like Photoshop.
But then doesn't the name seem a little odd?
It's terribly odd, yes, for that. I mean, I can imagine a special purpose function for the image case that says...
Well, it's in Paint.
Right.
It is there already.
Fair enough. Fair enough. Yeah, I mean, does this become a method for in Paint?
Not a method for in.
Why not?
Because it's function that are learning from some data. So
I understand, but if the default
trained,
if we've trained something on generic photographs, for example, then yes, use this for in Paint.
Definitely.
So one thing that comes to mind. So let's assume that we have an annotation system that is well designed and that works, which is not true at the moment. This data imputation, it seems like it could benefit from that, saying rather than just replacing missing values, like replace the data in this annotation with whatever.
Yes, exactly. Yes, I agree.
It doesn't seem to depend on the fact that data is missing.
Yeah, it seems to be the only thing you need to know is where. And
yes, where or what. Because again, that's the point. If we've got annotations, then we can remove based on annotation value. Look, okay. So,
I think what is interesting, but it's a little different. So that's like saying the blue things.
Yeah, it's like a green screen.
But that to me is a way of specifying where, kind of like the color neighborhood that got, it's. You see what I'm saying? It's a way.
Yeah, I see it. Right, but okay. So look, your basic point is which elements of the data are to be imputed.
Yes.
Right. By the way, is this notebook saved somewhere? Should I save this in?
No, it's not saved anywhere at the moment. I just created it and sent you by email.
Okay. Okay.
Can you tell me which folder?
I put it in neural net framework.
Okay.
Okay, impute based on Which elements of the data are to be imputed? That's the real question. I mean, it's interesting to use the word impute. If we could, okay, what would happen if we just used impute? It's similar to interpolate, right? So how does this relate? Actually, we call it interpolation, don't we? Interpolation, okay, so we'd say imputation, which would be like interpolation. So interpolation, you give it, you know, this, and it returns an interpolating function. Imputation, what will we give it? It would return an imputation function. Is that right, Etienne?
Yes. So it's actually the same.
Well, it's not quite the same because that has a what are those things called? A participle. Okay, so
actually, sorry, it will be imputer function. Sorry.
Okay, and so what are the other? Whoops.
But what is that? That imputer function is. So you don't get new data. That's something that you can then apply to your data. Is that right?
Yes.
Well, let's walk through what these actually have. So, imputation of data. No, the imputation could take a distribution and your example.
No,
this can also take data.
This will be impute. This will be impute. Impute can either directly impute or take a distribution.
Okay, but let's look at that as by analogy with interpolation.
Mm-hmm.
Okay, so imputation there would be examples. You know, a set of examples, or conceivably you could just give it directly the distribution.
I guess it could work like that as well. This would be.
So then it would be analogous to interpolation. So imputation. If I say range of 10, I'm trying to remember how this works. If I say 0.7, yeah, okay. So that's what, right. So then imputation by analogy would be imputation of the examples, comma, specific data. I don't know what we call it. The thing that we are imputing about. Data, let's call it. Well, let's call it input. Okay, and that would return output data, correct? It would return the post-imputation version of that input, correct?
Yes, we could do that.
And then imputation on its own of examples would return an imputer function.
Yeah.
What about the case where you are learning from the examples which you wish to impute?
So this would be impute. This would be the verb.
I don't understand that case. Oh, wait a minute. What?
It's you learn from the examples and you impute on the examples.
I see. That's a very weird verb for that. I mean, it's a self-impute.
I mean, it's a bit like, dimension reduce the data, impute the data. Find anomalies in the data.
It's a little weird. What would you say if you were making a longer name for this case?
Impute missing, maybe?
Because they have to have missing stuff, otherwise there's nothing to do.
Yeah.
But these things, even in this case, it has to have missing stuff or there's nothing to do.
Exactly. I think it's not too bad to add missing. I mean, it's clear. Otherwise, impute is obscure. And I didn't know what impute meant. I mean, I'm not English first language, but until, 2 years ago, maybe.
Yeah, I agree. It's an obscure word.
So missing impute, okay, it's related to missing. I understand.
And that's sort of the generally accepted term for it in the rest of the world.
Actually, a funny story. When I started doing the machine learning functions, I thought it was an N and not an M because it was too close to input. And so the first processors are called input.
Yeah, right. Well, it's a weird word. Oops.
Can you compare with, I don't know, input?
Let's compare with interpolate. Well, that's because it's a different meaning of the word impute. It is a different meaning.
Yeah, I think it's got a meaning like to give responsibility to.
Of course.
I think it's to.
I mean, I impute the thought to.
Yes, right.
Yeah.
But what I meant earlier was that missing data imputation, or I guess missing imputation, is in the machine learning community, people generally know what that means.
Yeah, I agree. Well, I mean, as a matter of fact, this is a strong argument against using the plain word impute. Not a single one of its meanings is useful here.
Agreed.
But with missing, it makes it acceptable, I think.
Well, so then let's go back to what you were proposing earlier. Missing imputation of data. Go ahead, Roger. Yeah.
So this is kind of a more global view. Let's say that I have financial data and there's missing data. Would you dare to use this function? If you're going to base models on the conclusion of your imputed data.
You mean because there was a holiday on a particular day and there was no price value, and you still want to use that as some boundary condition for a differential equation or something?
Yeah. I mean, there's other calculations that's going to, in fact, rely on that data.
So, I mean, do you use interpolation? Look, I mean, interpolation is an alternative to this kind of impute. I mean, interpolation is similar to this imputation, I think, except that it doesn't deal with probabilistic stuff. It just is saying, I've got this single, thing of data. Am I right? I mean, interpolation is an extremely junior version of imputation that doesn't allow probability distributions. It just is looking at the data itself and trying to fit it.
I think you're right. I think the probabilistic difference is a key difference. Going back to that financial data question of would you use this on financial data, what you would do is you do multiple imputation. So you take advantage of the fact that you have a probability distribution that you can sample from, and you'd sample multiple versions of your data set, and then run your analysis on each of those individual versions of the data set. And then you can look at the end and aggregate the results of those analyses and say, what is the variance in these analyses? And then you can use that.
I buy that completely. That makes perfect sense. That's a good argument. Who made that?
That's James.
Okay, that's a solid argument.
Okay, but let's come back here. Okay, so is there any alternative to the term missing imputation? I mean, it is a slightly weird word. I understand that it means something in the machine learning world. Is there any more common term for that?
Well, sometimes they're called missing data handlers, or they are.
Yeah, that handler is a different thing. That's what you do. Like if you're computing the mean or something, what do you do to the missing data?
Right. And there are more specific names for various, things that have been developed before this approach was developed, which is also stochastic. So in signal processing, for instance, for things like time series and other things, there is, it's called the smoothing problem. When you're allowed to use all the data around you to sort of, you fit the best possible model, and then you use the expected value that's going to be in there in between.
Okay, well, let's come back to the question.
So it's like a generalized Kalman filter.
You could also use words like missing data guess or missing data estimate.
Yeah, or fill in missing data. Of course, we keep on saying it doesn't necessarily have to be missing, right? It could be data you just don't want to use for some reason. I mean, you might want to remove the anomalous data, right? So in other words, you've got a measuring device, and the measuring device is usually measuring just fine.
Okay. But this is different. There's different thing. There's like sensor data as well. Like exactly as you say, the measuring device doesn't measure the pressure higher than
data.
So, yeah. So it's
So there's missing data. There's censored data.
The sensor data is a different thing.
Yeah.
Well, I'm talking about you've got a temperature measuring thing, and suddenly a dragon walks by and breathes on your measuring device, and so you get a stupid measurement. Well,
that's not censoring.
What is that?
Well, censoring is that you let's say that here's a concrete example. You do a set of trials, like medical trials, and then you want to figure out if it's changed the sort of death ratio. But by the time you conclude the trial, not everybody has yet died. They will eventually die. You just don't know when.
Yes.
It means that you have an open interval for your data. So you have some data, but it's like an interval or a range of possible values instead of a crisp data point.
Fine.
For anomalies, we also use outliers, right? Name outlier.
Yeah.
This comes down to the fact that there are multiple different types of missingness. So censored data is a type of missing data, and there's a whole bunch of literature on this. You get missing completely at random data, you get missing at random data, and then you get not missing at random data. And censorship, depending on the type of censorship, is either not missing at random or missing at random, as opposed to missing completely at random.
What do you mean completely at random? What does that mean?
So missing completely at random is if whether or not a value is missing does not depend on the value itself or any of the other values that are related to that value.
I see.
Then missing at random is when whether or not a value is missing doesn't depend on the value itself, but could depend on other values that are related to it. So in a multivariate analysis, maybe one of your dimensions is missing, for an example, and that missingness depends on other dimensions, but not the actual dimension that's missing. And then not missing at random is the case where the missingness depends on the actual value that is or isn't missing. And this is important to consider because different imputation methods are going to be suitable for different types of missingness or not suitable for certain types.
Yeah, the problem is that
that sounds like a slightly different meaning of censor.
Yes, slightly different meaning.
I don't know that it is because, here's what I understand for censorship. Let's say you've got some measurement of voltage and current, and the sensor breaks in the case when the voltage is too high and then no longer records currents when the voltage is too high, or maybe when the voltage is too high, it doesn't record the voltages properly. And so you're censoring the voltage.
I think it's a sensor with a C as a sensor with an S.
That example uses both words.
Yes, that was the first word.
But James, I think it's different. If the measurer breaks, then the data is missing afterward. But if the measurer has a maximum value, you cannot measure more than 100 degrees, and you reach 100 degrees, then you don't know. You just know it's above 100 degrees. This is what's called censored data.
Right, exactly, Etienne.
Right.
Which not really missing. And I think we don't need to represent censored data for us now. I want to say about missing at random, in missing imputation, we are going to assume that the fact that it's missing or not has no correlation with, so to speak, with the value itself or the other values. Because I don't know how we could do otherwise at the moment. Trying to mention that.
Okay, but that might change in the future. But okay.
So there's no dependency model, is what you're saying.
Yeah, I mean, the values are dependent altogether, of course, but the fact that it's missing doesn't depend on the values.
Okay,
you cannot say, it's missing, it was probably higher or something like that.
We need to represent you know, quotes missing, whatever that means, or AKA ignored data in both input and output, in both training and input, if I'm not mistaken. So in other words, that's arguing. So, okay, for the case of numerical data, we understand how we're going to do that. Numerical data, the most obvious way to do that is to have a raw missing sitting in there.
Although for performance purpose, we might want to have...
We might want to have it be different, yeah.
A packed array and then say there's a missing in position 4.
All right, okay. So then the question is, do we want to have a, what would we call it? Some kind of missing data wrapper where we have an object and we have something that says where things are missing. I mean, did you propose something like this?
Yeah. There's advantage of then we can plug it everywhere.
The thing, yes.
Now, of course, the question...
It's a weird word, but missing data is a weird word for this, you know, because missing, we already have the thing missing, which represents a piece of missing data. So what this is an indirect missingness thing. I mean, this is more like missing annotation or something.
Yeah, actually, if we have an annotation...
So we have a bunch of things, like we have weighted data, we have censored data, which are these kinds of things. You know what I'm saying? They have additional information associated with them.
Okay.
Oh, but then one question is, how do you combine these things?
Yeah, that's a good question.
Okay, so I don't particularly like using the term missing data for this thing here because it's really not, that suggests that this that we are presenting is the missing data, whereas we're merely saying where the data is missing. See here, weighted data, it's the data, but it's got weights. See what I'm saying?
Yeah.
What about masked data, where the mask indicates missingness?
Better, but I think it has the, you know, who is that masked man type I don't know. Masked data just sounds like, I don't know, it's, you know, password field that's doesn't give me the right emotional feeling, so to speak. Indicated. Let's see. I mean, and is it the case that we always want I mean, really, whether it's missing, which is kind of an emotive word, or whether it's merely being ignored is sort of irrelevant to us, except, as James has pointed out, whether it's used in the training cycle. Right? You get what I'm saying? It will be better to have a name
which doesn't have missing in it.
What's that? That doesn't have missing, which is why masked data would be, I mean, it's sort of ignored data or something, but that's not good either.
Just marking it. It might be like the marked data. You want to specify marked.
Yeah.
Unknown data?
Disregarded data is the more accurate term, probably. You see, ignored data suggests that this thing itself is the ignored data.
Yeah, it's like missing, yeah.
So what that would do is would contain data as is, and then some indicator of where it's sort of where it's.
I mean, the word ignoring might be interesting. It's a little weird to say missing impute of something with ignoring. I have a bad feeling we are not going to wrap this up here. I think we're going to have to continue because I'm really late for something else. Drat. Or do you think we are going to let me see. Do you think if we went on for another 20 minutes that we would be able to get somewhere here? I can push another meeting to a different time, or do you think we should try and pull this up another time? Roger, your experience with these things.
Yeah, I feel we are slightly close, but
I'm worried that this is really close to this annotation business, which we are close to figuring out, but we have not figured it out.
Right.
Because if we have the annotation stuff, then we've got a mechanism. We definitely don't want two different mechanisms for this. I think we can assume, for purposes of what you're building, Etienne and Amir, I think you can assume that your functions will be given, your inter functions will be given just locations where things are to be disregarded. And those locations may be found by basically saying, position of something with some particular value, or they may be found by being literally given those positions.
Yes, I think it would be simple to use something simple like that.
I do believe it will be to solve this sort of representation problem for big contiguous data and to not sort of use the missing wrapper, which is, as we already talked about, is very costly. It will be useful for quantity arrays and all kinds of other areas.
Yes, it would be.
And they might in fact use, I think the dual purpose thing that we talked about for annotations is to have sort of both a wrapper and an option when there is an object.
Yes.
Will be exceedingly useful.
I agree. I think things like Python, NumPy have got equivalent structures where if you have say masked data and take the mean of that, it'll ignore the things which are masked out. So
yeah, which we have versions of, may have for years. But the problem is that there are two cases here. Look, the two fundamental cases for annotation are, this is now, it's annotation from outside, annotation with annotated data elements, or it's annotation from outside are the two cases. And the annotation from outside breaks into the case where there is existing wrapper, there's an existing wrapper, and there isn't an existing wrapper. And you are applying something. So it's probably, what we probably want to say is, this probably wants to be annotate, blah, blah, blah. That returns a thing which is called annotated or some such other thing that contains the information, right? That's the canonical form where you could take. Well, actually, I'm sorry. I'm wrong about this. I'm wrong because this is saying there is an existing wrapper would be something like image. And then, as we said on the right-hand side there, annotation rules, arrow, whatever. Make sense?
Yeah. I do think we should continue this in another annotation meeting because I think that this is not going to conclude in time.
We had some suggestions from our live stream here. One of them is various people with suggestions about fill missing for the imputation stuff, or smart fill data. We have never used the word smart anywhere in our system. But I do think that concept of filling, auto-filling, is not a bad concept. For some, how do we feel about things like, it's not quite autofill, but it's also not quite smart fill. but it's the concept of filling. Thoughts about that?
I think that's what you say, filling in missing values.
Yeah, I think that makes sense.
I think that's a more mainstream terminology than impute missing values. Even if that's heavily used in the machine learning community.
So fill missing was another suggestion from the live stream, which is actually not bad. It's better. Honestly, it's better than impute missing.
Yeah, I prefer it as well. What would be there should be a verb and a sort of, I don't know how to call it.
A noun, I think.
Yeah, I think so.
Okay, so fill missing, this would be the analog of data impute.
Yeah, and the noun.
Well,
fill function. That sounds the imputer function.
Oh yeah, and the function, yes.
Fill function.
Fill function.
Not quite right.
Not quite right. I agree.
But hold on a second. What is the let's see. What's the other case that we need? We need one that is going to return. We need the self. We need the fill missing to a bunch of data that is where it's self-filling. So
yes, exactly. Which I assumed would fill missing B, and that's the one above that we should change.
I'm not sure. Is that really the
so before it was data, okay, it was missing imputation, so it would be more missing filling.
It's really weird.
Yeah.
But I like this idea of
missing fill. It will be missing fill if we follow the same pattern as we did before. Missing filling and missing fill.
And which one is which? Missing fill.
Yeah, it will be missing fill, missing filling, and missing filler function. That would be what we do normally for a supervised learning function.
All right. Until next time. Okay, so we should plan to reconvene soon about this. For those on our live stream, we actually have another live stream meeting coming up in about 20 minutes. So, all right, so we're going to wrap this up, and Sushma, you're going to untangle hopefully these various. Who is PMing the annotation thing? Do you know?
That is Bart.
I think that's weird. I think that made sense when it looked like it was a annotating front end elements, but I think you better take that from him, or he. Yeah, you figure out why.
We'll talk with each other and figure it out.
Okay, sounds good. Thanks to the folks on the live stream. Great suggestions, and thank you to everybody here. See you all soon.
Okay.
Bye-bye.
Bye. Bye.